Welcome back to ECE 501B. Our goal today is to finish Chapter 5, which means we have a lot of facts on upper triangular matrices to think about or work through. Your next homework assignment, homework 4, is due a week from today, and that one is dealing with Chapter 5 material, eigenvalues and eigenvectors. I'm actually going to start a little bit ahead of the material, meaning I'm going to give us an example so that we can start to be thinking about why these upper triangular matrices might be important. We'll start with an example, and then we will essentially step back and say, okay, so what? What is it that is unique about these upper triangular matrices that we are focusing on those? We will basically learn that an upper triangular or even a diagonal matrix, those are representations of these operators in a nice basis, meaning we are now moving or changing, let's say, the coordinate frame around so that we can now isolate on these operators that have nice representations. And by nice, I'm meaning we have a lot of zeros in the matrix representation. Before I slide a little bit further on our list of goals, it looks like we're dealing with the even numbered propositions. We have 12, 16, 18, and 20 to cover, but we're not just restricting attention to the even numbers. We will pick up an odd number, and we may not get there, but if we were to get to real vector spaces or what's possible in real vector spaces, all of these right now are dealing with complex vector spaces, and that allows us to make maybe what you could consider more desirable facts or statements. When we get into real vector spaces, we actually start to impose a few more restrictions. And with real vector spaces, I think you'll remember that we are not guaranteed of having an eigenvalue for, let's say, a two-dimensional operator. And the fact or propositions or theorems below this dealing with real vector spaces, what you'll want to be thinking about is if we have an even number for our dimension, then we need to kind of be careful because we may not be able to diagonalize or put this in an upper triangular form. If we have an odd dimension, then it might be possible to, or it will be possible to identify a real eigenvalue, but again, if it's 3, we may have a block upper triangular, meaning we may have a 2 by 2 submatrix on the diagonal that is associated with this 2 by 2 subspace that cannot possess an eigenvalue. Now, maybe that will be open for you because I don't know that we're going to get through all of this material, but what we want to talk about now really is focused on complex vector spaces. The proposition that we will start with is proposition 512, and it is talking about upper triangular matrices or representations of operators and invariants. What do we mean by that? Proposition 518 says that lambda, now lambda I'm referring to as the eigenvalues will be on the diagonal of an upper triangular matrix. That's one nice thing about a upper triangular. Now we can immediately find the eigenvalues of that operator. They're right on the diagonal. That's 518. 520 says if we have distinct eigenvalues, is it clear what we mean by distinct? Non-repeated. So we can't have an eigenvalue at -1 and another eigenvalue at -1. That would not be a distinct. When we have distinct eigenvalues and n of those, Nevada of those, which is equal to the dimension of our vector space, then we can actually diagonalize that operator, or the matrix representation of that operator, which really means that if we have n distinct lambdas, we have n distinct eigenvectors, or n linearly independent eigenvectors, and those can now be used to diagonalize our matrix representation of this linear operator. And the last proposition that I've outlined in our list of goals, proposition 521, starts to talk about this equivalence relationship between these different facts. Is a matrix diagonalizable? If it is, then your eigenvectors, all of your eigenvalues can be used, or those form a basis. You have n linearly independent, and they span the space, all just with using your eigenvectors. That's equivalent to having then a direct sum decomposition of your vector space V. And if the last statement or fact is equivalent to the middle one, then the last one is equivalent to the first one by this relationship of each of these being equivalent to others. Meaning, if you have a diagonalizable matrix, then you could say, oh, then I can have a basis formed from my set of eigenvectors. Or I can now give you a direct sum decomposition of your vector space. Remember, these are all dealing with complex vector spaces. Here's an example of an upper triangular matrix. I'm just going to quickly slide through this. This is on R3. I hope it's not too shocking that this is what we mean by an upper triangular matrix. Everything below the diagonal is 0. We could have zeros above the diagonal, but we definitely are having zeros below the diagonal of an upper triangular matrix. Either of those ones, -1 or 1, could be 0. That 3 could be 0. They could all be 3, or all be 0. It would still be upper triangular, but then it would actually be more specific. It would be a diagonal matrix. But right now, I'm just referring to this, or working right now with upper triangular matrices. All the entries below the diagonal are 0. The notation that I'm using is I'm saying the matrix representation of a linear operator T. The linear operator T is an operator on R3. That means it's taking a vector of reals that have 3 coordinates and mapping them back into that same vector space of 3 real coordinates. My basis is the standard basis, and in that basis, this matrix I'm saying is 2, 3, -1, 0, 4, 1, 0, 0, 5. If you ask me where that came from, I'll just say I grabbed it out of the air. It has no other significance. I just wanted to create or build an upper triangular matrix. And based on what we already have learned, what are the eigenvalues of that matrix? 2, 4, 5. We can't count very well, can we? But it's 2, 4, 5. They're right on the diagonal. And I'm just going to give you then the eigenvectors, and you should be able to verify this on your own. You should be able to find those. And the eigenvector W2, what do you know about that relative to a null space? Or can you make a statement about W sub 2 and the null space of some matrix? You know these eigenvectors. Well, if you can't quite think that far ahead, just think of the eigenvalue-eigenvector relationship. AW2 is lambda 2 W2. Now put all of that information on one side of the equality sign, and you have A minus lambda 2I quantity times W2 equaling 0. W2 is in the null space of A minus lambda sub 2I. all just coming from AW2 equal lambda 2 W2. Likewise, W3 is in a null space and W1 is in a null space, but they're in a null space relative to those eigenvalues. Do I have distinct eigenvalues? And are those eigenvectors linearly independent? Yes, because they each have a new coordinate or component that's non-zero, and they just sort of build. With this particular matrix, we can observe what happens with A operating on V1, our first, let's say, basis vector. The first basis vector is the x direction. The result of A V1 is we stay in that direction. So we are an element of the span of the x-axis, or we're in the span of V1. If we start in V1, we stay in V1. This Vegas concept. Not quite, but related. What about V sub 2? Now if we operate on V sub 2, which is the y-axis, now what happens? What's one way of describing that? If we start in y, where do we end up, or at least remain? Do we stay in y? Not necessarily, but we do stay in the xy plane, don't we? So we're staying in V1, V2. If you now take V2 and map that through A, you're staying in V1, V2. So V2 is basically in the span of V1, V2 through this linear operator. And finally, AV3 is in the span of all of R3. So if we start in Z, we're not guaranteed of staying just in Z, we're only guaranteeing that we stay in the XYZ plane. But that's sort of nice in this upper triangular matrix. We have this nested behavior of our set of basis vectors, or if we wanted to, of our eigenvectors. There's a nesting property. Let's now talk a little bit more in general about upper triangular matrices. That was the example to sort of get us thinking about what's going to happen. This is foreshadowing the rest of the lecture. It's really maybe introducing it before we've even defined it. A quick note on matrix representations. And a particular linear map. A quick note on a matrix representation of an operator. What do we know about an operator in terms of its matrix representation? Geometrically, if you said, oh, I have an operator, do you see a geometric object? It's a square, isn't it? It's not a circle, it's not a triangle, it's not a rectangle. Matrices are usually rectangles, right? But this one is now a specific rectangle, it's now square. And we really only need to specify one basis if we want to. What would be nice is to figure out what a nice basis, that one basis, might be. And that's what we are looking for. Looking to find good or efficient basis for this linear map or for the system. And our claim is that a good basis is one where the matrix representation of the operator is simple. And throwing around words like simple or nice or good, those are a little bit subjective. The meaning is if it's simple, that means lots of zeros. And lots is also sort of a relative term, but that's as good as we're going to define. What do we already know about these matrix representations and having a simple operator? Let's try to recall what we've already learned. Results we've already developed are sufficient to show that for a finite dimensional complex vector space, and that C in the middle of those 5 consonants is important. So we're really stretching Vanna on this one, VDCVS. To show that for a finite dimensional complex vector space, there is a basis where the matrix representation of the linear map T, or the linear operator T, is matrix of T is lambda, 0, 0, everything else below lambda in the first column is 0, and everything else in that matrix is a star, meaning it's arbitrary. So based on what we already have developed, we know that we can create a matrix representation for a linear operator, and here it's on a finite dimensional complex vector space that has this structure. Where did that come from? Here is sort of a couple of facts that justify that, or a very rough proof. Previously, we proved that this linear map or linear operator T, what do we know about an eigenvalue of that? Do we know anything about whether this linear map has an eigenvalue if it's on a complex vector space, finite dimensional complex vector space? Did we show that it has at least one eigenvalue? Previously, we proved that this linear operator T has at least one eigenvalue, lambda, and an associated eigenvector. Let's say V. And 2, we previously proved that we can always extend a linearly independent list of vectors into a basis. We can always grow this list of linearly independent vectors far enough to make them a basis. So we previously proved can always extend a linearly independent list of vectors on this finite dimensional complex vector space. Now, let's just think about what we have. Suppose that I just said, in general, what do we know about a matrix representation of a operator, linear operator? We could write that as some linear combination of the basis vectors that we're using for that linear map. And here I'm not going to worry about what's over there. But in our case, we've already learned that we have an eigenvalue, lambda, and an eigenvector v for that particular linear operator T. If that's the case, and we are going to extend V, we just have one vector right now. Let's build up and add on n minus 1 more linearly independent vectors to form a basis. Now let's look at TV, and we will call those additional vectors W1 through W sub n minus 1. And we now know that the matrix A is some linear combination of those basis vectors, where this is now A11, A21, AN1, this is A12, A22, etc., AN2, and we just keep going. This is A1N, A2N, ANN. This is our A matrix, and before we hadn't explicitly identified what those second column through the last column of that A matrix were. We just had it as an asterisk. But now what do we know about that first column in this A matrix? If lambda and V we know are an eigenvalue and an eigenvector for this linear map T. What can we say then about this A matrix? Can we make it a little bit more specific in terms of, can we identify any of those coefficients that are in the A matrix beyond just saying they're these arbitrary coefficients A sub ij, and in particular the first column. Now I'm wanting you to tell me, is there anything that you can say about A21, and we'll show that in just a minute. Hopefully. What do we know about TV if V is an eigenvector of T? And the eigenvalue of that eigenvector is lambda. So now we need TV to actually equal lambda V, don't we? And we have the V. We only need to pick that one up. It can't be a linear combination of the other basis vectors, W1 through Wn minus 1, by the way that we created V, or the way that we assigned V. And so it's now the only way that we can build that. We have the first column in this right-hand side being V times A11, A21 times W1, A31 times W2, etc. But we know that it has to only have V as the vector that is a linear, or it's only contained in the linear combination. So we know that A, the matrix representation, is lambda, and all the other entries in that matrix are 0, and the others we're not going to keep writing. That comes to us in the following way. So now we're remembering how that could be done. Remember that the kth column of this representation for A is the result of applying T to the kth basis vector. TV sub k. In this case, it's just TV. And in our particular case, we defined the first vector in our basis to be the vector V. Our first vector is the eigenvector V, and it has the following representation in terms of the other basis vectors. If I now said, okay, write V as some linear combination of V, W1, W2, W sub n minus 1, the only way that you're going to build that up is you're going to say, well, let me put a 1 there, and a 0 there, and a 0 there, and zeros everywhere else to scale those other W's, since V is equal to V. These are the basis vectors. And we know that TV is equal to lambda V for V an eigenvector. Or, that is, we've shown that A11 is equal to lambda, and all the other AJ1s are equal to 0 for all I, or for I equal to 2, 3, up to n. And that's what we were trying to show. We were trying to show that TV is equal to lambda v in this particular choice of basis, and that now tells us that we actually have lambda on the diagonal. Below that diagonal is all zeros, and now we're on our way to maybe thinking about, oh, can we sort of generalize this idea? Now can we start with this submatrix that's square in this starred place and continue with that process, or repeat that process? And hopefully you can now see that when we're living on a finite dimensional complex vector space, we can start to come up with more than just this one diagonal entry being non-zero and everything below it zero. Meaning we can do even better than what we just did. And that's what's leading us then to this concept of an upper triangular matrix. An upper triangular matrix is one where all of the elements below the diagonal are zero. So that now we have a lambda 1, a lambda 2, a lambda sub n. We don't care what's up above, but everything below are zeros. Now we're in a position to start talking about some of these facts or propositions relative to having upper triangular matrices. Let's now look at proposition 512. Suppose we have a linear operator T on V, and now let's assume that we have identified n vectors for that, and let's say that those are actually our basis vectors. If T is a linear operator on V and V1 through V sub n is a basis on V, we can actually conclude that the following statements are equivalent. First, if we now have this matrix of T on the basis V1, V2, V sub n, and now with that basis, let's say that that matrix representation is upper triangular. That's the first statement. The matrix representation of T is upper triangular. And we know what that looks like. And we may call that UT, upper triangular. Now that statement is equivalent to T V sub L, meaning mapping V sub L, the vector V sub L, through the linear operator T keeps us in the span of V1, V2 up to V sub L for each L. meaning if we take V1, then TV1 is only going to be in the span of V1. V2 is going to be in the span of V1 and V2, and that is equivalent to the matrix being upper triangle. And we've already shown that in the first example that we started for today. We can also say that those two statements are equivalent to the span of V1, V2 up to V sub L is invariant under this linear operator T for each L equal to 1, 2, up to N. Is it clear what we mean by invariant? If I said, let's say that N, little n is 5, then if I give you little n equal to 3, what can you tell me? If the A is true, what does C tell us? If we have an upper triangular matrix representation for this linear operator, what does that tell us if I now say, oh, let little l be 3? So now if I tell you little l is 3, then if we have an upper triangular matrix representation for that linear operator, that says that if you give me anything that's in the span of V1, V2, V3 and operate on that with T, we're going to stay in that same span of V1, V2, V3. If I give you little l equal to 4, then you give me a vector that's in the span of V1 through V4, operate on it with T, and you'll stay in V1 through V4. If I give you something in the span of V1, then you're going to stay in V1. That's what statement C is really sort of saying. Pardon? It's not a diagonal, it's UT. It's upper triangular. So now let's see if we can justify the equivalence of these three with a proof. So we're saying that you have a basis that allows a linear operator to have a matrix representation that's upper triangular. Now, in terms of those basis vectors, they are special in the way that they are capable of basically decomposing this vector space. Now you can start having invariance within collections of these eigenvectors, or I'm sorry, of these basis vectors. We're using these as basis vectors. So now let's look at a proof. And now the first part of the proof, I'm going to show the equivalence of A and B. A and the arrow is going in both directions. So that's meaning I'm looking at the equivalence of statement A and statement B. So now if I look at part I of this proof, I'm first going to show that A implies B. And then obviously for the second part of this part of the proof, I'm going to show that B implies A. But now let's look at A implies B. And first let's consider this matrix representation of the linear map T. So now we're assuming A is true. A is upper triangular. And what does that mean? That means that the nth column of this matrix representation of T is the expansion of T v sub L in terms of the basis that we are using. And the basis that we are using, this was given in our proposition, that's V1 through V sub n. If we're starting with an upper triangular matrix, that imposes some specific structure on that matrix. The nth column of an upper triangular matrix, what does that look like? If I said, okay, you have an upper triangular matrix, extract the nth column of that, what does that look like? Let's say that here are the top L elements. This is the nth column, and here are the n minus L elements. This is an upper triangular matrix. I've now walked over to the nth column, and what can you tell me about this partition or the entries relative to that partition that's labeled or that's drawn at the base of the nth element? What's happening below that? It's all 0 below that. And above it could be anything. Meaning, let's now just rewrite that as a sub 1L, a sub 2L, down to a sub LL, and then we have 0 below that. Now, the nth column of the matrix representation of T is the expansion of T v sub L in this basis V1 through V sub n. This is now how the scalars that I use to scale those basis vectors to give me the representation of T v sub L, which says that I now use a sub 1L. That scalar is scaling V1. A sub 2L is scaling V sub 2. And that just keeps going. I have plus a sub LL times V sub L plus 0 times V sub L plus 1 plus 0 times V sub n. What does this mean about the representation of that nth column of, or the expansion of T v sub L? T v sub L is now written as a linear combination of the first L basis vectors, V1 through V sub L. This means that T v sub L is expressible in terms of only V1, V2, V sub L. Or, stating that another way, thus, T v sub L is actually an element of the span of V1, V2, V sub L for any L. And that's then saying that if we have an upper triangular matrix, we also have statement B, which says that TV sub L lives in the span of those first L basis vectors. So now A implies B has been shown. What about B implying A? So now this is part, well, no, let me just say that this is for A implies, or A if and only if B, and then part 2 of the proof will be B if and only if C. How's that? So now I need to show in this top part B implies A. We're given now that TV1 is contained in the span of V1. That's in our statement B. Statement B also says that TV sub 2 is in the span of V1, V2. And that just keeps growing. We now know from statement B that TV sub L is contained in the span of V1, V2 up to V sub L. We can rewrite that. We could say then that T, V1, is some scalar combination of V1. That's what being in the span of V1 means. And actually, let me scale or label that scaling with 2 subscripts, alpha 1, 1. What about T, V sub 2? We now know that that could be some linear combination of V1 and V2 since it's in the span of V1 and V2. What about T, V sub 3? Now that's equal to alpha 1, 3 V1 plus alpha 2, 3 V2 plus alpha 3, 3 V3. And that just keeps continuing. We can now build up or say that the linear map acting on or applied to V sub L is some linear combination of the first L basis vectors. And now we can just place those coefficients in the appropriate location in our matrices, or in our matrix representation. We can now say that, oh, we now know that the result of that is going to be alpha 1, 1 and zeros. The second collection was alpha 1, 2 and alpha 2, 2. And nothing else. And likewise, alpha 1, 3, alpha 2, 3, alpha 3, 3, etc., down to alpha sub 1L, alpha sub LL, and eventually we have alpha 1N all the way down to alpha sub NN. And I hope you can see that that matrix representation of T is upper triangular. So now we've shown B implies A, we just earlier had shown that A implies B. Now we know that A is equivalent, or if and only if B. And that's part one of our two-part proof. Now for the second part, what we want to work on is B if and only if C, or B implies C and C implies B. Let's work with the latter. Suppose that C implies B is the direction we want to pursue first, and we'll show that by a contrapositive proof. Which means, what are we going to do now? What do we assume, and what are we trying to show in a contrapositive proof? So now I'm basically starting at what I'm trying to end up with, and I need to take, and now I'm saying assume the negative of that, or say not B, and show that that statement, not B, implies not C. If I can show that, then I've shown that C implies B by a contrapositive proof. What's not B? B was dealing with this spanning, or this spanning relationship. T v sub L lives in the span of all of the basis vectors up to and including v sub L. If that's not true, then we are making the statement that if T v sub L does not belong, or is not an element of the span of V1, V2, V sub L, and that's what we're assuming for each L, then the span of V1, V2, up to V sub L is definitely not invariant, because for that map to be invariant, it has to map it back into that set of vectors. And now we're saying it doesn't. So if not B, which is T v sub L, is not in the span of V1 through V sub L for each L, then the span of V1 through V sub L can't be invariant, because T acting on a vector in that set of spanning vectors, V1 through V sub L, actually produces a vector that's not in the span. Of those L vectors. And that's our proof by contrapositive, or that's using this contrapositive argument to show that C implies B. Now we need to show that B implies C. And then we'll be finished. Suppose that we have B. So now we're assuming B is true. If B, then C, and what was C? C said that the span of those L vectors is invariant under T. But if we have if we have B, that implies C by the invariant property of T. So if B, then C by definition of invariance. Meaning, if we sort of walk this out a little bit, we have TV1 is in the span of V1. TV2 is in the span of V1 and V2, and that just keeps going until TV sub L is in the span of those V sub L. Therefore, this list of basis vectors, V1 through V sub L, is T invariant. Which now says that B implies C, which now shows that we've established the equivalence of B and C, and that now is the end of the proof of the equivalence of those three statements if we have a basis where the matrix representation of the linear operator is upper triangular. Then we can start talking about these invariance properties and TV sub L living in the span of those earlier, or this nesting concept of these basis vectors. Let's now look at, we may not go through too many more proofs, but let's examine some more statements or propositions relative to upper triangular matrices. Examine statements about upper triangular matrices. And you can refer to the textbook by Axler for the proofs. Theorem 513. Suppose we're given V, and again we are assuming that that's a complex vector space. And we have a linear operator T, then there is a basis on V or of V where the matrix representation of that linear map has upper triangular form. So you give me a linear operator on a complex vector space, I can find a basis under which the matrix representation of that linear operator is upper triangular. What you don't want to do is assume that that's true for all vector spaces. And in particular, this is not necessarily the case that you can create an upper triangular matrix representation on a real vector space. Not necessarily true for a real vector spaces. And now just think of that two-dimensional example of a rotation. That didn't even have an eigenvalue. So if we didn't have an eigenvalue, we can't find it on the diagonal of one of these matrix representation. So now if we do have an upper triangular matrix, what can we now think about in terms of this structure? Think about the form of the matrix. The matrix representation of this linear operator T is now lambda 1, lambda 2, lambda sub n. It's upper triangular, so we have zeros down here, and we're not worried so much about what's up there. The fact that the first column has only one non-zero element means that the first vector of the basis is in fact an eigenvector of T by definition. And what's the eigenvalue? It's lambda 1, the way we've defined it. So that now we have lambda 1, lambda 2, or just demonstrating this, star 0, 1, 0, that TV is equal to now lambda 1 times 1, 0, up to 0. But if T has no eigenvalues, which is in fact possible for reals, and think of that rotation example now, then it must follow that that linear map T, or that linear operator T, on this real vector space has no upper triangular form. And we know that's the case, or can be shown. I can give you a two-dimensional real vector space that's has a linear operator on it that's just a rotation, and you can't find an eigenvalue, a real eigenvalue, and so you cannot make that matrix upper triangular by any kind of basis. Let's look at proposition 516. This says if we have a linear operator T on V, and that linear operator has an upper triangular matrix representation, if T is a linear operator and has an upper triangular matrix representation, then this linear operator T is invertible if and only if all the diagonal entries of the upper triangular matrix are non-zero. So now if you have an upper triangular matrix representation, you can look on the diagonal and quickly, if any of those are zero, you know that linear operator is not invertible. If they're all non-zero, they can be negative, they can be positive, they just need to be non-zero, then you can invert that linear operator. That proposition, 516, leads to one of the key results of the chapter 5. Which is proposition 518. Suppose we're given a linear map or a linear operator T on V, which has an upper triangular representation on some basis. The eigenvalues of that operator, T, are the diagonal entries of the upper triangular matrix. And we've been saying that all along. But let's just sort of convince ourselves of that. Suppose we now take V1 through V sub n as our basis, and on that basis we have an upper triangular matrix representation of the linear operator. Take V1 through Vn as the appropriate basis. That is, we have the linear operator T on V1 through V sub n is now lambda 1, lambda 2, lambda sub n, arbitrary above, 0 below the diagonal. Let's now take lambda to be a scalar in our field. So in this particular proposition, we haven't said anything about complex or real vector space. We've just said, suppose you can find an upper triangular representation on some basis. Then the eigenvalues of that linear operator are on the diagonal. So now let's look at the matrix representation of T minus lambda I in this same basis, where now we have, the only thing that we've done is we're subtracting lambda on the diagonal. So we now have lambda 1 minus lambda, lambda 2 minus lambda, lambda sub n minus lambda, Haven't done anything on the off diagonal and nothing, or we haven't changed anything on the off diagonal below or above. Now let's remind ourselves of what happens to the eigensolutions. Eigensolutions are associated with the null space of T minus lambda I. And if we have a non-trivial null space, then that means something about the injectivity or non-injectivity of that map, which means we want T minus lambda sub I to be injective or non-injective, to have a non-trivial null space. We need it to be non-injective. If it's not, then our null space is trivial. And that's not what we're after. But remember what other relationship we have relative to a linear operator in terms of those three equivalent relationships between injective, surjective, and invertibility. But also remember that for operators, injective if and only if surjective if and only if invertible. So now what we are saying, so this is equivalent to saying we want T minus lambda sub I to be non-invertible. But our previous result shows that for an upper triangular matrix to be invertible, or upper triangular matrices invertibility, was if and only if, what do we know about the diagonal matrices? They're non-zero. So we have non-zero elements on the diagonal. Thus, lambda is equal to lambda 1, lambda 2, lambda sub n are in fact the values that make T minus lambda sub I non-invertible and hence are the eigenvalues of our map T. So now what we want to do is talk about, or what I'm going to tell you to pursue, are the results that remain in Chapter 5 dealing with diagonal matrices, which now we can show if we have a linearly independent set of basis vectors. Well, that's by definition linearly independent and spanning basis, which is our eigenvectors. We also want to look at proposition 520 and 521. And some of these results for real vector spaces, which now we can't continue to assume that we have upper triangular matrices when we're dealing with real vector spaces. We may not be able to even find eigenvalues for 2 by 2 submatrices within these linear maps. So the next time I want to start in Chapter 6, which is now dealing with inner products, which tells us or allows us to be talking about lengths and angles in these vector spaces.